Okay, today, guys, we're going to talk about Taylor and Mclaren series. These are two, well, basically, they're both Taylor series, but a Mclaren series is just a specific type of Taylor series. So we're just going to do a little bit of background on the way it is, and then we'll try to work with a few of them, or I should say where it came from, and then we'll try to work with a few of them. And that might be the first part of this video. I maybe might have to cut the video short and make two, otherwise it might end up being like an hour-and-a-half video. So first we're going to kind of say, so far you guys know we've been working with, so far we have been working with functions of the form 1 over 1 minus f of x. So everything we've done, we've been, forcing this situation to happen. Of x to the n, right? Or I'm sorry, f of x to the n. So that's kind of where we've been stuck. We've been creating power series like that, but it's only of a specific type of function. It has to be written in a certain way. So what about all the other functions like sine, cosine, tangent, e to the x, natural log, all that stuff? And other functions in general, harder functions. We're going to focus on kind of those style, but there are worse ones out there, obviously. So what if we kind of assume, okay, let's assume that everything could be represented as some kind of a power function. Okay, so we're going to have this f of x equals c sub 0 plus c sub 1 times x minus a. And this is just a power function being generated centered at, x equals a. So let's assume that x equals a, because we want our power series to start off as the, worth the same as the original function. So we're going to assume x equals a. And something that makes it a good power series where we feel good about it is if it represents the function pretty well and it takes on similar characteristics of the function. So we mean in for our class, we're going to focus on the derivative. So that means that the derivative of this should help us build a better power series. Okay, so we should be able to take the derivative of our function and take the derivative of the series, and that should create something good if in fact it was a good power series. So the idea behind this is if we let x equals a, that means that f of a is equal to c sub 0 plus 0 plus 0 plus 0, so on and so on, right? So then that means that f of a is equal to c sub 0, okay? So that's a good starting point, all right? Now what if we take the derivative of f of x, so that means f prime of x is equal to c sub 1, because this would now cancel, right? Because that was a constant. So c sub 1, let's see here, plus 2 times c sub 2 x minus a, right? Plus, and then we will have 3c sub 3 times x minus a squared plus 4c sub 4 times x minus a cubed, right? So I just took the derivative of each term. So that would be 0, that would be c sub 1, that would be 2 times c sub 2. Take the power, put it in front, reduce the power by 1. And then the derivative of the inside is just 1 because each one is an x minus a constant, a. So we know if we do f prime of a, well, that would be f prime of a is equal to c1. Because if we plug a in here, if we plug a in here, we plug a in here, those will all become 0. So the only thing left standing will be f prime of a. Oh, I'm sorry, will be c of 1, c sub 1. So then, what if we took the second derivative of x? So then this guy would now cancel, right? And then this would become 2c2 plus 6, oops, let me write this correctly, plus 3 times 2c sub 3 times x minus a, plus 4 times 3 times c sub 4 times x minus a squared, plus so on and so on and so on, okay? And then we know that f prime of a would be 2c2, okay? So here's the thing. if we wanted to, we could solve for C sub 0, C sub 1, C sub 2 in all of these problems. So we know that C sub 0 is worth f of a. But here we know that C sub 1 is worth f prime of a, right? And this one we could solve and divide by 2, right? And we would have C sub 2 is worth f prime of a over 2. Wait, was that supposed to be double prime? Yes, I made a mistake right there. Sorry about that. That's actually a double prime. Please fix that. So then this would be f double prime of a. So we now know that C sub 1 equals f prime of a. We know that C sub 0 is equal to f of a. So if we go back and we look, these are the coefficients right here, right? I'm able to write the coefficients in terms of f of a and f primes of a, okay? So that leads us to something called the Taylor series, okay? Where the Taylor series is a series, a power series, right? But the coefficients that are in front are based on the derivatives, okay? So if you notice here, we have, right? And technically there's an x minus a to the 0 power there, right? But we don't write it because anything to the 0 power besides infinity or 0 itself is 1. So this would be f of a over 0 factorial. This would be f prime of a over 1 factorial. And remember, this is the first power, second power, third power, fourth power, so on and so on. And these are the coefficients of these polynomials. Now, this power series is being written out x minus a, but we could plug in a for anything. We could plug a to be 2, so then it would be x minus 2. We could plug a in to be 3, centered around 3, so we could do x minus 3, x minus 3, x minus 3 squared, x minus 3 cubed, so on and so on. So this formula is a way that we can generate a Taylor series, okay, centered at any value x equals a, as long as, you know, it is valid at that point. So the thing is there's Taylor series are really nice when a is equal to 0, okay? So when you say that x minus 0 is just x, you get a special type of Taylor series, which is a Maclaurin series, okay? Oh, and by the way, this notation right here, that just means how many derivatives, the first derivative, the second derivative, the third derivative, as many as you want up until approaching infinity, okay? So like you could technically write this as f sub 3, or I'm sorry, f of 3 of a. That actually means the third derivative of f at a, okay? So that's just a notation thing, okay? So we're gonna look at something very special to Taylor series called the Maclaurin series. So again, a Maclaurin series is really just a Taylor series, okay? Except instead of being centered at any value, it lets a equals 0, okay? So we're gonna look at a Maclaurin series, so a Taylor series centered at x equals 0 is called a Maclaurin series. So it's just a special type of Taylor series. And it looks like this. F of 0 over 0 factorial plus f prime of 0 over 1 factorial plus f double prime of, oops, I'm forgetting an x right here, sorry about that, plus f double prime of 0 times x squared over 2 factorial, so on and so on and so on. There's no x minus a, because if you think about it, x minus a would be x minus 0, which is just x. So this makes it a very nice and clean series. Okay, so we have that. So what we would want to do is I guess you could memorize them. You may want to memorize these particular Maclaurin series because it makes it nice. So we have this and we have this. So I could say find the Maclaurin series of f of x equals e to the x. So kind of an old-fashioned way to find, instead of just trying to look at this formula and plug it in, well, we need those coefficients. So we're going to just think about it like the old-fashioned way. We're going to say, well, let's do f of x, let's do f prime of x, let's do f double prime of x, and you just build a few terms until you kind of can see what's going on, okay? Now, the nice thing about e to the x is the derivative will not get out of control, right? We're going to have it really nice. And then we're going to say evaluated. And we'll just have each one of these evaluated at the same value. I'll just do this so I don't have to write it all out. And this will be 1 and 1. Oops. 1, 1, and 1. Ugh. Let me just try to clean this up a little to make it look a little nicer for you guys. So 1, 1, and 1. So we know if we put 0 in for our x, we're going to get, we know that we're going to get 1, okay, for all of these. So then that means I can rewrite this if I use this idea right here. If I use this, right, if I use this, then I can rewrite this as e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, so on and so on and so on. Okay? Now, in case you're wondering how I did that, all I did was this told me that these would be the coefficients in front. See right here? This is my coefficient, this is my coefficient, this is my constant, this is my coefficient. But in this case, f prime of 0 would be 1, f double prime of 0 would be 1, f triple prime of 0 would be 1. So notice these are all ones on top. Or I guess I could write it if you want to see it more like I had written up above. I could write it as 1 over 2 factorial times x plus x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th, so on and so on and so on, okay? So technically then, if we wanted to write this as a series in summation notation, we could say that e to the x equals the sum from n equals 0 to infinity of x to the n, and notice, look at the powers. This is x to the 0, x to the 1, x to the 2, x to the 3, so on and so on. So that is actually x to the n, and then it's divided by n factorial. Well, then I just write this, n factorial, and we now have the way to write a power series for e to the x, okay? Now again, if the fact that it was a Maclaurin series and x equals 0 or centered at 0 made it really, really nice. Okay, that's what makes it so clean. Let's look at it. Hold on real quick. Okay, so sorry about that. My dogs went crazy, or my neighbor's dogs actually. So let's take a look at another problem we've been working on. So using Maclaurin series, find 1 over 1 minus x, okay? So find the power series for this, or I should say use the definition of Maclaurin series to find the power series for this, or the Maclaurin series. So we already know how to do this, but I just want to show you guys that we could just do over this. We could write over here f of x, f prime of x, f double prime of x. Normally I like to do 3 derivatives just so I can kind of see things a little bit better. So f of x equals 1 minus x to the negative 1, right? That's what it really is. Take the power, put it in front, rewrite the inside, reduce the power by 1. Let's do the chain rule. So this will be negative 1 minus x to the negative 2 times negative 1. Okay, so this would be actually 1 minus x to the negative 2, right? Because the negatives will cancel. Then we can do this will be negative 2, 1 minus x to the negative 3 times negative 1. So this will actually become, let's see here, 2, 1 minus x to the negative 3. Does that seem right? Yeah. And then let's do another one. Let's see, this will be 3 times 2 times 1 minus x. That'll be a negative 3 times 2 times 1 minus x to the negative 4 times negative 1, but that'll be 3 times 2 times 1 minus x to the negative 4. Okay, so those are our derivatives. And then we can evaluate it at x equals 0. Oops. Oof, it's really bad. I don't think we need that much, but I'm just going to write it. So let's use x equals 0. So then we'll get, when we plug 0 into this, we'll get 1, right? When we plug 0 in for this, we will get 1, right? When we plug 0 into this, we will get 2. And we plug 0 in for this, we will get 6, right? So now, if I want to try to, use the same formula that I did for e to the x up here, I do f of 0 over 0 factorial, f prime of 0 over 1 factorial times x. So I'm just going to use that same formula. So I'm going to say f of x equals 1 over 1 minus x equals f of 0 over 0 factorial plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 times x cubed all over 3 factorial, okay? So let's just see if this actually worked, right? So if we take f of 0, that would be this guy, right? So we get 1, okay? Now we plug in 0 into f prime, but that means we still get 1, right? Divided by 1 factorial times x plus f double prime, which would be 2 over 2 factorial, which would be x times x squared, plus 3, wait a minute, where am I at here? F triple prime, no, this would be 6, but isn't 6, this is really 3 times 2 over 3 factorial, but that's literally what 3 factorial is 3 times 2 times 1 times x cubed, so on and so on and so on. So look what we generate. So we created this power series. We created this polynomial, right? This is our basic general power series that we already knew how to do. We already knew this is what it would be if I had just done our old technique. Remember where we said 1 minus 1 over x is just equal to the summation of x to the n of n equals 0 to infinity. This is the same as this, okay? So we could use a Maclaurin series. So it was cool that we could do it previously, but now we kind of have like this stronger way to generate power series, okay? So the Taylor series is much, much stronger. And in general, we kind of feel like it can create a power series for anything if we're good enough at finding the derivatives for it, okay? So that's that. Now, I want you guys to try to find the power series, find the Maclaurin series for f of x equals cosine of x, okay? So take a minute, pause the video, kind of build like I did, do f of x, f prime, f double prime, f triple prime, maybe even for this one, f quadruple prime, You might need to do more than you used to do, and just kind of write it out and set it up and see what you get. Okay, so you guys are back now, so I'm going to go through and work out the problem how I would do it. This is like the slower way to just kind of see what everything is doing. And I'm not too scared about multiple, fourth, fifth, sixth, seventh derivatives, because it's a cosine, and I know that it's just going to alternate back and forth between sine and cosine. I just got to be careful of my plus and minus signs. So we have cosine of x. The derivative is negative sine x. The derivative, second derivative of the cosine of x would be negative cosine x, right? Because the derivative of sine is cosine. Then the derivative of this would be positive sine x. Then the derivative of this would be cosine x, okay? Now I have to evaluate this. So I'm going to evaluate it. X equals 0, right? Okay, so let's see what we get. So we're going to say x equals 0, x equals 0, x equals 0, x equals 0, x equals 0. You guys can obviously skip a lot of this stuff. I'm just trying to show you kind of where everything's coming from. And the result would go here. So cosine of 0 would be 1. Sine of 0 would be 0. Cosine of 0 would be 1, but there's a negative in front. Sine of 0 would be 0, and cosine of 0 would be 1 again. So these are our coefficients. Remember, these are the coefficients that go in front of the x terms. So now I'm going to write this. F of x equals cosine of x. X equals 0. This is centered at x equals 0. Let me write this over here. So then we're going to have f of x equals cosine of x equals, now remember, it says that you're supposed to do f of a divided by 0 factorial, so that would be 1, plus f of a, or f prime of a, okay, which is this, right, divided by 1 factorial times x, so this would be 0 times x, plus, well, actually, it's going to be minus, right, because it's a negative 1. So minus, and then this will be x squared over 2 factorial, and then this will be plus 0, and then this will be minus, oops, no, it's plus again, plus, that would be what? This will be 0 times the x cubed term over 3 factorial, and this will be plus 1 times x to the 4th over 4 factorial, so on and so on and so on. So if we really look at what we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And then what do you think the next term would be? It would be x to the 6th over 6 factorial. And the next one, x to the 8th over 8 factorial. Do you see the pattern? And that's the hope, right? Because a series can't hide from you. It's a pattern, right? So we should be able to rewrite this in summation notation. We should be able to go from 0 to infinity. Now, we have to account for the alternation. So we would go from negative 1 to the n. Let's see here. Yeah, when you plug 0 in, you get a positive. So we're okay on that. And then how are we going to generate x to be squared, all the multiples of 2, 2, 4, 6, 8, 10. Well, that would be x to the 2n divided by, what is this, 2n factorial? Oops, I wrote that ugly. Like that. And that is our power series for cosine, okay? So I'm going to give you guys the interval of convergence for these. So let's see here. Let me kind of write this list for you then. So these are what I would memorize if I were you. I would memorize these Maclaurin series because it'll make everything much easier for you. So you know, we already did 1 over 1 minus x. We know that this is equal to the summation of x to the n and equals 0 to infinity. And we know the interval convergence for this guy in general is from negative 1 to 1 in general, okay? So let's do another one. Let's do e to the x, we just did. e to the x will be n equals 0 to infinity of x to the n over n factorial. And the interval of convergence for this is from negative infinity to positive infinity, meaning that this is a good representative of the function if you give me an infinite amount of terms, pretty much everywhere, okay, on the number line. Then we have cosine of x. We can have a good power series for this, or Maclaurin series, I'm sorry. Same thing, really, but of infinity, built differently. There we go. And this is x to the 2n over 2n factorial. This has an interval of convergence of negative infinity to infinity. Okay, let's do sine of x. And this would be n equals 0 to infinity of negative 1 to the n. I'm not going to go through and do this one, but it would be done in a similar fashion to n plus 1 all over 2n plus 1 factorial. And this has an interval of convergence. And then we have arctan. Let me just finish writing this out for you guys. N equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1, but no factorials, okay? And this has an interval of convergence to bracket negative 1 to 1 close bracket, okay? So these are kind of your go-to moves from Maclaurin series. So if you can ever find something and have it written like this, you can just jump straight to the answers. So these are your series now, right? These are now the series representatives of these functions when you're centered at 0 for working with the Maclaurin, okay? These are ones that you, if you were taking the test in class, you would have to have those memorized. Since you're taking them at home for this particular, because of the C19 thing, you're going to be having them right next to you on your desktop. So, you know, hopefully you'll know how to use them, not just memorize them. But in general, that's the goal, okay? So let me see here if we got one. Let me see if I have one I want to go over with you guys. So let's say that I had, no, we'll come back to that one. Maybe I'll do that one in the homework. Let's try this one. Let me just show you guys something. So suppose you want to use this new information. So it says using a Maclaurin series. You know, find the Maclaurin series for f of x equals tan inverse of x squared. Okay, and these are the primary ones up here, guys, that I'm going to ask you. Yes, there's more, obviously, but these are the ones we're going to work with in this class. Okay, and so we can use some information that we know. We already know that tan inverse of x, when you're working with Maclaurin series, is equivalent to n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1. We know that fact already. Now, the only difference is we're not dealing with arctan of x, we're dealing with arctan of x squared. So literally all you do is you say, well, tan inverse or arctan of x squared, you just plug in x squared everywhere you see an x. And that's it. So I just took x squared and I plugged it in right there. And now I'm going to get the series n equals 0 to infinity of negative 1 to the n, x to the 4n plus 2 all over 2n plus 1. And that's it. That's all there is to it. That's why memorizing these can let you do much more complicated and difficult functions. All right. So let's move on. Let me see if I have one I want to work with on this. Yeah, let's look at this one real quick. And remember, even though we're dealing with Maclaurin series, that's technically really a Taylor series, right? So if it works with Maclaurin, it should also work with Taylor, because a Maclaurin is just a specialized one. Those are just easier ones to remember. Okay, so now let's say that I gave you use a known Maclaurin series to find, oh no, let's do this, to evaluate the integral from 0 to 1 e to the to the negative x squared dx. Okay, so this is a pretty difficult problem. This comes in like multiple parts. Okay, so we're going to use a known Maclaurin series to evaluate the integral from 0 to 1 of e to the negative x squared dx. Okay, now we know that Maclaurin series can be a good representative of e to the x on the entire number line. Okay, so we're going to kind of work with this on e to the negative x squared. So first we have to generate e to the negative x squared. Well, we know from looking up here, e to the x is just x to the n over n factorial. So I'm just going to say this is the series negative x squared to the n over n factorial, right? Because that's all we did in the previous problem. So then that means this is actually negative 1 to the n x to the 2n over n factorial. Okay, negative 1 to the n x to the 2n over n factorial. And I got that information using this fact. So this fact gave me that, right? I know that's true, x to the n over n factorial. We just proved it, we found it, but here's the formula for it. So now I can move forward a lot quicker than I would have had to if I had to generate all this from scratch, right? Because I would have needed to take the derivative of e to the negative x squared, the derivative of that, the derivative of that, the derivative of that, generate a pattern and kind of see. But I'm already jumping ahead of the game. I already have my series, right? So now I can write this as an integral. Let's see here, times the integral, or equals the integral of the summation of n equals 0 to infinity of negative 1 to the n x to the 2n over n factorial. Okay, now let me see, let me make sure I didn't mess anything up. Okay, so we're good. So now we got to integrate the right hand side because we can't integrate the left. We, use substitution doesn't work. Maybe this is a very difficult integral. This looks like one that we would have a really hard time trying to integrate. So the best we could do is try to approximate it or something. Well, a good way to approximate is to build a series, because a series writes out terms, and then maybe we can go back and use our remainder theorem from alternating series. You never know, okay? So let's see what this would be. This would be n equals 0 to infinity of negative 1 to the n. Now, when we integrate this, this is going to become x to the 2n plus 1 divided by 2n plus 1 times n factorial. Right? So we get x to the 2n plus 1. Okay. There's another way you could also have done it. You could have chose to write out these terms. Right? Let me, I'm going to go ahead and write it like this. It's kind of bad notation, but I'm just going to do it for now. We could have chosen to write it out. We could have wrote out the terms and then integrated term by term, because remember, a series is just addition, right? I could have also chose, I've seen some people do it this way, where you'd plug 0 in, right? And you'd get 0 to the, so you'd take the integral, and then we'd have, what is it? It's going to be 1 plus x squared over 2 factorial. Oops, that'd be over 1 factorial. Sorry about that. 1 factorial plus, let me see if I plug 1 in. Okay, so this would be x to the 4th over 2 factorial now. Minus, I think there's a minus in here somewhere. I think this is a minus. I think I messed that up when I plugged in the 1. So then this would be back to minus again. This would be x to the 6th over 3 factorial plus x to the 8th. This isn't the way I normally do it, but or sometimes I do it this way, but so this is n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, and then, you know, minus, and then so on and so on and so on, right? And then we would eventually have to integrate this, right? So this is the integral. So if we were to integrate it term by term, we would end up with x minus x cubed over, what would this be, 3 times 1 factorial, plus x to the 5th over, what would that be, 5 times 2 factorial minus x to the 7th over 7 times 3 factorial, so on and so on and so on, right? And then we would integrate that from 0 to 1. Now, I hope you guys can already notice a couple things are happening. We're getting an alternating series. If we come over here, we could do the same thing with where I integrated the series itself, not the terms of the series. So let's do that. Let's see what this would be. So this would be plug in 0, so we'd get, that'd be x to the 1 divided by 1 factorial, or 0 factorial, which is 1. Okay, and then let's plug in 2, or I'm sorry, plug in 1. That would be minus x to the 3rd over 3 times 1 factorial. Let's plug in 2. That would be positive x to the 5th over, and then let's see here, 5 times 2 factorial minus x to the 7th over 7 times 3 factorial. Do you see the pattern? They're identical, right? Because there's no difference in what we're doing. One of them is integrating the terms of the series, which is addition or subtraction, and the other one is integrating inside the series, which still produces the same series, okay? So, and then this guy is going to go from 0 to 1, okay? I choose to do it the way that's in blue, but you guys can do it in the way that's in red. They both work, okay? So what we're going to do is, what kind of error do we want? So we're going to say, let's say evaluate correct to within an error of 0.001. So we have to find a term. Remember, this is the term, or this is the value that we need to find a term smaller than. So what I'm going to do is I'm going to write out the first few terms, right? So luckily, once again, it's f of b minus f of a, so we don't have to use the 0 because 0 will wipe everything out. So I'm going to write out some terms. This will be 1 minus 1 over 3 plus, what would this be, 1 over 10 minus 1 over, was that 42, plus 1 over 216. Let's see, we probably need actually a couple more. Let's do to the 11th, or I'm sorry, to the 9th. I think that would be, wait. So this is x equals 1, 3, 5, 7, 9. So let's go one more, minus, I'll add another term to this, plus x to the 9th over 9 times 4 factorial, minus 0 to 1. And then this will be 1 over 9 times 4 factorial. So 9 times 4 times 3 times 2. So we get 216. Oh, I already did that one. And now the next one would be the 11th term, I guess, which would be 1 over 11 times 5 factorial. So I get 1320 for that one. So we need to find a term that is less than 0.001. So I'm going to do 1 divided by 216. That's 0.004, so that's still a little bit bigger. So let's do 1 divided by 1320, 1,320. So 1 over 1,320 is equal to 7.5757. So let's just do this. Times 10 to the negative 4. So that's equivalent to 0.000. Well, I guess that's exact, but this is going to be approximately 0.0007577, so on and so on, right? So that means that this guy is in fact less than 0.001, and he is the first term that is less than 0.001. So that means that this is my error term. And everything before it can be used to add it. Now, we can go through and prove that this is a convergent alternating series. The limit of this would be 0 because if you take the limit of n times n plus 1 times n, or I'm sorry, n times n minus 1 times n minus 2 times n minus 3, you're going to get a massive n. So we're going to end up with that being a convergent alternating series. So over here, we know that this is a convergent alternating series. We know it's decreasing. Each term is getting smaller. So this is a convergent alternating series, right? Now the thing is because it's an convergent alternating series, and we can now use the error term to help us approximate the sum, that means that these terms are the sum. So our sum is approximately 1 minus 1/3 plus 1/10 minus 1/42 plus 1/216. So let's see what that is. Okay, so I get a very small decimal, or I should say a really ugly fraction. So I'm going to say that this is approximately you know what, I'll write it as a fraction just to give it a little bit of exactness. 5651 divided by 7560. And we are within 1 over 1,320th of the true sum. So we didn't actually find the actual sum, but this is an approximation of 0.7474867725. So this is an approximation to the sum, okay? And we know that we are within 1/1320th of the actual sum. We don't know plus or minus, but we know that we're within that amount. So we're pretty darn close to the actual sum, okay? Within 0.00757 of the actual sum, okay? So that means it's really good. So if you had to bet, you'd be pretty sure that the sum is pretty close to 0.747. You're not exactly sure what it is, but you know it's pretty close to 0.747, okay? Because there's 3 zeros here. So it's not going to do too much to mess with that. I guess the 4, if you added it, would put it a little over, but you guys get the idea. So this is how we can use alternating sums and Maclaurin series to help us evaluate integrals that we kind of can't do. So we still can find the sum, and you could write computer software to do stuff like this as well. And that's probably what your calculator will do also, okay? So this is the general idea of Taylor and Maclaurin. I'm going to probably make a little short video on Taylor polynomials. So you can use Taylor polynomials and, you know, however many terms you want to do it, but just kind of look at what we're building here. You guys see how this is all x cubed, x to the 5th, x to the 7th, x to the 9th, so on and so on. These are polynomials. They have weird coefficients, but they're really just polynomials. So oftentimes when you're dealing with a polynomial like x minus 2 to the first, x minus 2 to the second, x minus 2 to the third, we call those Taylor polynomials. So I'll probably make a little short video on that, and that'll be it for the course. All right, you guys, I'm going to end it so you guys have a chance to watch this video, but thanks for watching.